Hello, my name is Malcolm Griffiths. I'm retired from Chalk River Laboratories and I'm adjunct professor at Queen's University and Carleton University in Ontario, Canada. I'm going to share with you today some of my thoughts on diffraction in the TEM based on the accumulated experience I've had during my career. What I've done recently is created a book, An Engineer's Guide to Nuclear Reactor Core Materials. And in chapter 4 of that book, I talk about characterization of microstructures. And I didn't want to get into too much detail when it comes to the theory of diffraction in the TEM, especially the TEM, although I do cover X-ray diffraction quite extensively. I make the point that transmission electron microscopy using electrons or electron diffraction is more complicated than X-ray diffraction because of the interaction of the electrons. They're charged particles, waves that interact much more strongly with matter than do X-rays. So I thought I would follow up and actually give you my thoughts on electron diffraction and how it should be treated. Okay, just by way of introduction, if you're not familiar with an electron microscope, this is a schematic diagram of the two most important modes in an electron microscope. One is the imaging mode, where we have a defect. We shine electrons through a thin foil, and we can create, with various lenses, we can create, or not we, I don't create it, but the microscope creates this beautiful image of the internal microstructure. You'll notice that I've highlighted the lines or the electron paths that come out at specific angles. This is the diffracted X-rays. I'll talk about what I mean by diffraction during this presentation. But in the image mode, they go through a series of lenses and are manipulated in such a way as to produce a magnified image of the particle, of the sample, or of the microstructure within the sample. Whereas in diffraction mode, we're interested in collecting information about the angle at which the electrons are scattered from the material, and collecting that at the backfocal plane of the, or an image of the backfocal plane of the objective lens, giving what is called a diffraction pattern. Now, the diffraction pattern literally is the Fourier transform of whatever this is, whatever is in the sample. So in this particular case, it's really the Fourier transform of the planes. So this distance here is proportional to the inverse spacing of the planes, atomic planes in the crystal. And it's a very useful method for navigating around in orientation space, for tilting the crystal and understanding where one is, and for setting up particular diffraction conditions to give you information about the microstructure. Just for completeness, I put in an example just showing over here what X-ray diffraction is. I'm not going to talk about X-ray diffraction other than to say X-rays are weakly interacting with the material. And for all intents and purposes, for X-rays, we just have a lot of them, and a few of them are scattered at specific angles. And we're interested. And generally, what one detects is based on only single interactions, single scattering events. And it's not the same as electron diffraction, because the information we get down at the bottom of the microscope is the result of multiple scattering events through the crystal. Before going into the theory of diffraction, I want to recap from chapter 4 and 5 of the book a little bit about why one needs to analyze, or why would want to use an electron microscope to analyze microstructures. Most of my career I've worked on zirconium alloys, and zirconium is a hexagonal close-packed material, and one of the characteristics of the material itself, the fundamentals, is that it's an anisotropic structure. And when it comes to radiation damage, there are two forms of what we call dislocation loops, or in cold work materials, loops can appear as helices that climb on existing dislocations. But for all intents and purposes, I'm just going to focus on discrete loops in this particular case. And by and large, when you create point defects by atomic displacement, the vacancies tend to cluster together, or there are instances where vacancies cluster together in a platelet here, typically on the basal plane. Well, not very much so on the basal plane, giving a defect structure which is characteristic of these vacancy loops. And the important thing is that why this is important is that they're both sessile, harden the material, but they also result in contraction of the lattice when they're accumulated. Enough of them are accumulated. Conversely, interstitials tend to form on prism planes, so that's the displaced atoms themselves, and this gives you an expansion perpendicular to the prism planes. It's a little bit more complicated than that, because depending on the temperature, depending on the alloy, depending on a number of different variables, for the prism plane dislocation loops, accumulation of point defects on prism planes, we often get a mixture of interstitial and vacancy type defects. So whereas vacancy loops tend to be exclusively on basal planes, the prism planes can be a mixture of vacancy and interstitial. So if I used to think about a prism plane, for instance, in zirconium, typically we would get a mixture of loops of this type, where the vacancies are simply like a hole in the lattice on one plane, and the interstitials are like sandwiching a platelet on the same plane. Now, to formalize the characterization, how do we know whether it's an interstitial or a vacancy? We need to look at the displacement of the lattice caused by these loops. And to do that, the common methodology that's adopted is the finish start right hand convention, in order to define what the Burgers vector of the dislocation loop is. So what we do is you draw what's called a Burgers circuit around a dislocation in the loop, noting how many atomic planes you cross, and likewise for the interstitial loop. And then you draw the same circuit, basically count related to the number of planes at which you cross in a perfect crystal. And then you look at where you finish, and you take the vector between the finish and the start, and that defines the Burgers vector for the loop. Here it is basically cribbed out of a book by Mike Loretto. Consider the line direction for a loop is positive in a clockwise sense when viewed from above. Draw a circuit from the atom to atom in a clockwise sense, looking in the positive sense of the dislocation. Reproduce the same circuit in a perfect crystal. And the closure deficit from the finish to the start defines the Burgers vector. So by and large, what that means is an interstitial loop tends to, when one is defining the Burgers vector in this sense, the interstitial loop has the Burgers vector pointing upwards, and the vacancy loop has the Burgers vector pointing downwards. So when it comes to defect analysis, we're look at that. That doesn't come out very well. Inside-outside contrast. We use a method called inside-outside contrast analysis in order to define or to decide whether we have an interstitial or a vacancy loop. At the bottom here, we see a situation, or I've shown a situation where at the Bragg condition, where we're getting strong diffraction from the atomic planes, if we're looking at the planes which are perpendicular to the, parallel with the Burgers vector, there's actually zero contrast. There's no distortion on these planes. And so that's what's called, in fact, a G dot B zero condition. And that's the same whether it's an interstitial or a vacancy loop. But this condition, by knowing what the diffracting vector is for these planes, what the planes are, and knowing that we have zero contrast, you can actually define knowing what G is, if you like, and I'll tell you what G is later. Knowing what G is, we can define what B is. But let's say once we have that information, one can also be interested in the character of the loop. So which direction is the Burgers vector B? So this top diagram illustrates how one sets up the conditions to determine whether a loop, a dislocation loop, is an interstitial or a vacancy. And it has to do with setting up the diffraction conditions so you're just slightly away from what's called the Bragg condition. And I'm going to have to assume that you understand what I mean by the Bragg condition, but I'll be talking about the Bragg condition shortly. Basically, you set up an angle with respect to the planes of interest, diffraction planes of interest, which is slightly greater than Bragg. And the distortion of the planes around a dislocation loop is such that you get a rotation, bringing the planes into the Bragg condition. And at that point, you will see a strong contrast, and we'll see that dark image, which is characteristic of the edges of a dislocation loop in an electron micrograph. If we reverse the side of the planes at which we do that, this bending will occur on the other side. So by reversing the sign of G, the diffracting vector, we can switch between outside contrast in this case and inside contrast in another case. So this just shows that for a vacancy loop, for this condition, for the diffracting vector pointing in this direction with respect to the Burgers vector, we have inside contrast. And for an interstitial with a diffracting vector pointing out in this direction with respect to the Burgers vector, again, we don't know the sign of the Burgers vector, but this method allows us to determine what that is. We end up with contrast on the outside of the loop. Just a point to note is using the convention established by Mayer and Ayer and followed by Mike Loretto, the deviation on the Bragg condition is described by what's called a deviation parameter, S. And in this condition, when we deviate larger than the Bragg condition, we've rotated the crystal relative to, I'm going to talk about this in a minute, Ewald sphere. We've rotated it so that the deviation parameter for the diffracting vector, the perpendicular to the planes, is upwards. And that's defined as S positive by both Mariner and Loretto. So that you can see how when, in this case, for this setup, when the crystal rotates, shown by this red arrow here, what actually happens is that you lower this, or you reduce the distance between the what would be the diffracting vector and the Ewald sphere. The plane is brought into the Bragg condition. You're basically rotating this arrow, this G vector now, so that it comes into contact with the Ewald sphere and gives strong diffracting. For this particular condition, S is positive and we have weak diffraction, but when the planes rotate, the diffracting vector, known by G, also rotates. We're rotating the diffracting vector, we're rotating the normal to the plane, and we bring it in coincidence with the Ewald sphere, and then we get strong diffraction. So I've stated that here so you can picture that. I've talked about two things that are the Ewald sphere and Bragg diffraction, so I will be explaining them a little bit more. But for those people following this, you probably know what these what that is, what Bragg diffraction is, and what the Ewald sphere is. So you can create images of dislocation loops and also being able to characterize them. So here's just a nice image because it's clean of dislocation loops in neutron irradiated titanium. And by tilting around in the electron microscope, I can deduce what the loop configuration is, how the loops are lined up in rafts, and what their relative orientation is. But I can also deduce what the character is by doing that G dot B analysis I just showed you, and this just shows a typical set of images one would use to do that. And the key pair here is the bar 1 2 bar 1 2 1 bar 2 1 bar 2 pair, where if we look at these loops, the loops here in this layer, this raft, they're outside contrast. They exhibit outside contrast. They're bigger here than they are here. And this just shows what plane they're on. And this is just shows that when one tilts from this orientation, close to the basal orientation, up to a prism orientation, these loops, which are you can barely see because they're mostly edge on at this point, they open up and they become more elongated. So they're actually quite elliptical, and that can be confusing because even if you had a circular loop and you looked at it at an inclined angle, it would look elliptical. But if the loops themselves are also elliptical in the beginning, you have to be aware of what you're dealing with. Very briefly, I mentioned the knowing the sense of the loop by tilting from one orientation to the other, and that's very important because if one is looking at inside and outside contrast, the little black lines here denote where the contrast is strong for the conditions shown with G and S positive, the G in this direction and S positive. There is whether you show inside contrast as in this case or outside contrast as in this case for the same type of loop, It very much depends on the sense of the tilt of the loop. So you have to know what this sense is. And if you're far enough away from being close to edge orientation that it's very clear what the sense is, you can use one particular method of loop analysis, which is that by Mayer and Ayer, and I'm not going to go through that. You can read about it if you want. And when the loops are inclined to the beam direction, typically one would use a Follen-Wilkins method. But this just shows how the planes, the strongly diffracting planes, where they sit relative to the dislocation cause of the dislocation loops. This is a glide cylinder, so it just shows how a loop of a certain Burgers vector can move around, can glide around on its glide cylinder and have different orientations, different configurations. So you have to really understand and know where the loop is, how the loop is moving, both what its relative shear is, because you can have a certain Burgers vector and the loop can be sheared with that, given that Burgers vector, and it can have very many different orientations as a result of that shearing. But then you also change the orientation when you use different beam directions. So you have to be aware of what you're talking about, of what the situation is. Again, I don't want to get into too much detail because you can read about it in the various either textbooks on electron microscopy, but these are the papers that define these two methods. In the book, I talk about an interesting problem, just by way of one of the things that Elsevier wanted or encouraged is to show case studies. So in the chapter, when I'm talking about characterization and I talk about dislocation loop analysis, I decided to put in a case study, which is the related to the characterization of basal plane vacancy loops. And these are the little blobs here, the dark blobs here, you see here. They're absent in this here, they should be here and here, showing zero contrast, and they're present here and show outside contrast, which is consistent with dislocation, with faulted dislocation loops, as opposed to these other loops here, which are perfect prismatic loops. Now, the reason I showed this as a case study is the characterization can be ambiguous. And when I reported this, when I was a student of Mike Loretto's, I reported these loops as half 000 bar 1 because I couldn't tilt. I wasn't sure about what the loops looked like at a key part that would distinguish between whether the loops were this Burgers vector or this Burgers vector. Now, in my naivety at the time, for whatever reasons, and when I come back to it years later, I think, oh, I'm horrified, and think, oh my God, why did I say that? Because what I should have done is I didn't know, and I should have said it was that or that. And anyway, I go through the logic of why in the book, why it's really that or that. And then looking at my old images, I'm inclined to err on the side of, well, it's probably likely this one. It's a faulted bar 2 or 2 bar 3. Now, I tried to contact Phil Mag to let them know and create a correction, if you like, an erratum. And the erratum would simply be said, instead of being definitive that this is the character, that it's actually this or this. And they just made it so difficult. I just didn't know how to submit an erratum so many years later. This was in 1984. So I've given up, and I've put it in the book. And if you care to look at this later on, this is part of that the diagram showing how the loops they're not gliding now because they're fixed, they're faulted loops, so they're on a fixed plane. But we can look at or imagine what would they look like if they did, if we sheared over the planes that relative to the plane of the loop, and in that case the contrast becomes apparent. And actually, this one I can say that this is the loop that becomes more is the one that is the characteristic Burgers vector. So that's just an aside, just to recap on why I would be interested in diffraction analysis, and that's the case in that particular case. That's the case because I want to look at loop characters. But let's go now to the more general aspects of TEM and diffraction principles. So I showed you the ray diagram of an electron microscope earlier, and the important part, the guts of it, are what happens in the backfocal plane of the objective aperture, of the objective lens, sorry. So that's where we would insert an aperture. And I mentioned how the electrons come in. The dotted lines here are planes. I should have mentioned earlier that the diffraction angles, based on the wavelength of electrons, the Bragg diffraction angles, the characteristic angles where you get a strong scattering of electrons, is very small in electrons. For typical electron voltages between 100 and 300 kilo electron volts, and they're often a fraction less than 1 degree. So they're a fraction of a degree. And these diffracted planes come out at different angles, and we can collect the intensity from diffraction at certain angles and focus that what would be the points here. So everything coming out at this angle here is focused at this point, everything going straight through is focused at this point, and everything going out at the red angle here with this lens is focused at this point. So we can create images by selecting the intensity at different points on that backfocal plane. So in this configuration, we see a bright field image. We look at the electrons directly passing through the crystal, and we throw away anything which is essentially diffracted, scattered off at one angle or another. And that shows up as a dark, as a deficit, a dark image in an otherwise white background. But we can tilt the beam so that the one of the diffracted beams, now this one, the one coming out at this angle, goes down the optic axis of the microscope, and that creates a negative image of this one, which is what we call a dark field image, and that would be a bright field image. Another common mode that one would utilize is a high resolution. We want to get as much information as we can to create an image, in this case of atoms. Because of diffraction effects, when you have a small aperture, there's spreading of the beam, interference peaks, and that dictates the theoretical resolution of the image. And so one wants a nice large aperture to improve that resolution. And I'll talk a little bit about that later, and what affects resolution in the electron microscope and the scanning microscope. So basically, by having a larger aperture, and in fact as larger electron energy as you can, which basically produces a smaller wavelength, we have the possibility of high resolution imaging. And this now comes about, we have to take into account the interaction of the different phases coming at different angles in the image. So I talked about Bragg diffraction. That's very important when it comes to electron microscopy and the analysis of defects. But some of you may not be aware of it too much, and some of you will know what Bragg diffraction is, but irrespective, here's a reminder what Bragg diffraction is about. If we have a coherent wavefront, parallel wavefront, interacting with a material with atoms arranged here in a regular array, there are a number of different things we need to consider. First is that the angle of incidence, if we set up the imaging, or if we're interested in a condition where the angle of incidence is equal to the angle of reflection, that's the case where, the optimum case where radiation being emitted, I should get the pointer here, radiation being impinging on any point on the surface, when it's reflected off, it will be in phase so long as the angle of incidence is equal to the angle of reflection. In addition to that, if we look at waves that are scattered from atoms deeper within the crystal, there's a certain condition where you will get coherence, or if you like, superposition, strong superposition between the waves in the two reflecting from the two different layers. You will get that condition where you get maximum superposition, and a maximum, the signal occurs at a specific angle. So whereas for X-rays, I should point out that this, for X-rays in particular, this condition is not real. You never get a parallel, coherent wavefront like this. What you can do is improve the chances of getting some waves which are coherent as they come in and parallel by both collimation and by the number of photons that you use. So you have the numbers are on your side. Some of the photons will be coherent and parallel, and that's what you rely on. In the case of electrons, we have a better chance of getting that situation, because by choice of the electron emitter, we can have an emission source which is coherent from the outset, as opposed to X-rays, which is more of a random generation of photons. So, and because with electrons in a microscope, we can actually focus the waves and make them parallel, so that we get to this nice condition. So that we have this ability, because they're charged particles or charged radiation, we can steer the electrons with electromagnetic lenses. So when it comes to Bragg diffraction, there's a characteristic wavelength for the incoming radiation, and at a certain angle, if you follow the wave train here, there's a certain angle that that waves that are reflected off different planes here are in phase. So long as the wave, if we consider waves that are in phase to begin with, and that they're in phase when we're reflecting at the same angle, and then we look at the waves that are scattered at a certain angle, we get constructive interference for a very specific angle, and that's where the path difference between this waves that are on this wavefront that are parallel, the path difference is one whole wavelength. Now, in this case, the path difference between when this wave is at this point, when this wave is being reflected off the top surface, and then this wave is also reflected off the next layer down, this path difference, we have this and this going from C to B to D, in which case this has two, there are two wavelengths involved. When it comes to the Bragg law, this condition then applies the value, or the order of the reflection, what we would say would be n is equal to 2. There are two path lengths or two wavelengths involved in the scattering from the two different planes, and this distance here is d, which is the plane spacing times sine theta, and the Bragg equation is simply n lambda is 2d sine theta, which is simply just the condition geometrically where we get the waves are in phase when they're scattered from the two different layers, which are separated by a distance d. So another way to think about this is to say that diffraction, or to know that diffraction space is the Fourier transform of real space and vice versa. So what do I mean by that? Well, this is the Bragg equation rearranged in a different way. And we can call 1 over d, call it d star. We call it, and that's actually a vector in reciprocal space. And we can call the 2 sine theta over lambda another vector g, which is the diffracting vector or the wave vector. They're actually coincident, and the direction of d star in what's called reciprocal space, and I'm going to talk about that in a minute, which is a direction perpendicular. Reciprocal space, just very briefly, reciprocal space is comprised of building up a series of the Fourier transform, a series of points in this space which has a direction which is perpendicular to the planes and a distance or a vector magnitude which is the reciprocal of the plane spacing. So in an electron diffraction pan, what we have is a diffraction spot, because we're really building up a picture of diffraction of reciprocal space, a diffraction spot which is at a certain distance in the diffraction point given by d star, which is also equal to g. So we can refer to this g star as a reciprocal lattice point, or a wave vector. And I'll talk about that a little bit more as we progress here. So let's move on. Well, in order to formalize discussions of reciprocal space as it relates to atoms' planes and the spacing of the planes, I just want to recap now about indexing of planes in crystals. Anybody who took physical metallurgy courses at university or anywhere else or on YouTube would know that one can define the index of planes if we have a coordinate system x, y, and z. X, y, and z. We can and we have a crystal structure, we can look at, and if we're looking at a unit cell of that crystal structure, we can define planes within the crystal where we have high densities of atoms, and we want to index those planes. We want to know what their orientation is and what their spacing is. And we do that by drawing the plane in the crystal. This is a cubic crystal here, taking the reciprocal of the intercepts of the plane with the crystal, and then reducing it so it's in an integer form. So this plane is 1, 1, 0. Because if this is my lattice and my unit cell is defined by A, B, and C, the 110 plane intersects the B and the A axes at a value of 1, and it doesn't intersect the C axis at all. So that's 1 over infinity, and when it's reduced, it becomes 0. So we have a 110 plane. If I looked at the plane which was half the spacing, it would be intersecting it halfway along here, and that would be 2, 0. And to show that, illustrate that, here we have a 1, 2, 0. So a 100 Miller indices spacing would be this, something that intersects at along in the unit cell at A, at the distance of A from the origin, from some atom on the corner of the unit cell. But in this particular case, we've chosen a plane which is halfway along, and in that case, the intercept is 1 over 2, and we end up with an index of 200. Likewise not likewise, but for in hexagonals, it becomes a little more complicated because we have this anisotropic structure with a unique C-axis. It is isotropic within the basal plane, but we have this basically anisotropic crystal structure, and then it becomes more complicated. So you will probably come across what's called a Miller-Brave indexing. And what that is that we can work with a 3-index system, which is the Miller indexing system. Let's say we have use the axes A1 and A2 and the C-axis coming out of the paper. That would be the Miller indexing system. But for various reasons, for obvious reasons, another index system that's possible, that's commonly used, is the Miller-Brave indexing system, in which case a third axis is introduced, A3. And then we do the same kind of manipulation where you look at the intercepts with the different axes. And where that is of benefit is that if we're looking at planes, let's say the planes here which are parallel with the C-axis of the hexagonal prism, so the prismatic planes, if we're looking at the prismatic planes, then in fact we're looking at the prismatic planes which are perpendicular to each of the unique the axes defining the hexagonal cell A1, A2, A3. If we're looking at those planes, in the Miller indexing system, they would have different sets of indices. So you would look at A bar 1 bar 1 O, for instance, which is the perpendicular to the A3 axis, and you wouldn't necessarily know that it's the same type of plane as O10, for instance. But when you use the Miller-Brave indexing system, they're all the same, just different combinations of the same indices. I mentioned reciprocal lattice. good to know what the reciprocal lattice is so that you understand when I'm talking about it. But for those of you who maybe not so familiar, what it is in a nutshell is that one can build up a lattice in space which is made up of vectors, points in space, which are defined by vectors, which are given by the perpendicular to a set of planes, and the spacing, or sorry, the length of that vector is equal to 1 over the spacing. So the reciprocal of the spacing between the planes in a direction which is perpendicular to the planes. So if we were to imagine a lattice in space built up of these vectors, you can see that we have a in this case, like this G vector here would come out here and would be represented by a point in space, a reciprocal space. And this G2 would be another vector over here, represented with this reciprocal space. The beauty of the TEM is that it samples reciprocal space. So instead of reciprocal space being this imaginary, no, not even imaginary, it's not, it's real, but it's actually, there isn't a set of points in space except that we, by relating this focused point in an electron microscope and relating that to the angle at which the incoming wave is diffracted, we can define what is a reciprocal space vector, which is this one. So when you look at the wave vector, if we define the wave vector of the incoming radiation by K0 and the scattered vector on Bragg diffraction, they would have these vectors. And the difference between the incoming radiation and the scattered radiation is actually the G vector, which is the reciprocal lattice vector, which would show up in the diffraction pattern. Lot to assimilate there, needs some thought, and I'm not going to dwell on it any further except to wish you luck. So one can formalize the reciprocal lattice, and this is just standard textbook stuff coming out. The most important thing I want you to appreciate is that if we have if you like, a vector in real space which defines the unit cell, let's say the A axis of the unit cell, and we take the dot product with the A star, which is the reciprocal space vector corresponding to the plane which is perpendicular, the Miller indices that would have a Miller indices corresponding with A, 1 or 0, for instance. When you take the corresponding reciprocal lattice vector corresponding with that plane, if you like, it's always 1. So we used reciprocal lattice vectors in order to manipulate or to put in mathematical form what diffraction is. I'm going to introduce another concept which is important, and that's the concept of the Ewald sphere. The reciprocal lattice is something we can imagine, put in and what we're doing in the TEM is we're sampling the reciprocal lattice. So it doesn't exist until we set up the diffraction conditions for each lattice point, so that we see the effect. We can, if you imagine a whole series of points in space, or in the reciprocal space, we can sample that reciprocal space by varying the angle at which we're sampling by keeping the angle of incidence equal to the angle of reflection, we vary the angle of the incoming radiation, but keeping in mind that the outgoing radiation is sampled at the same angle. And this, what the Ewald sphere construction does is that if we put our crystal at the center of the Ewald sphere and look at one point where the Ewald sphere intersects what we call the reciprocal lattice, this would be the origin, which would correspond to the direct beam. So we start here, and it turns out that if we take a vector from the origin to some reciprocal lattice point corresponding with diffraction of a particular angle, a particular Bragg angle, we excite that reciprocal lattice point for a particular geometric configuration of the crystal, given the wavelength coming in and sampling the wave going out. And that's the Ewald sphere construction. Again, something to go away and think about, or to look up on YouTube or something else like that. Here again is just another example of the Bragg condition that we're talking about. I should mention that these reciprocal lattice points correspond to the Bragg condition, and we have different series of superposition for different orders of reflection, N1, N of 2. In the electron microscope, where the reciprocal lattice becomes very evident, is in the diffraction pattern. So we have a electron beam coming down through the crystal. We have planes in the crystal which are scattering the electrons, and at certain angles we get very strong diffraction. Now, the Bragg condition is only achieved where the wave vector, if you like, the scattering that defines the scattered wave, where it intersects the Ewald sphere. My reciprocal lattice point doesn't necessarily have to be on the sphere to show up, because the reciprocal lattice point is not actually a point. It's broadened. It's broadened in directions which are perpendicular to distances, real distances in space. So while the points themselves have a spacing which is the reciprocal of the plane spacing in directions perpendicular to the planes themselves in the crystal, there is also broadening because of the dimensions of the crystal. So this is what's called domain size broadening, or coherent diffracting domain size broadening, and some of you may know it as particle size broadening. So we get this broadening effect, and what that means is that there's a point, even though we might not be at the Bragg diffraction condition, we will still be sampling or having the condition. If we use the Ewald sphere construction, there's a condition where we're getting some diffraction due to the intersection of the broadened peak with the Ewald sphere. And what that means is that we're sampling numerous points in diffraction space. And we actually see a range of angles, we can call it angular space, wave space, reciprocal space, whatever you want, but it corresponds to diffraction angles, and we see a range of angles instantly all at one point, especially if we're on a zone axis. But so the angular range over which we can sample the reciprocal space is improved by what's called spiking. And this is great because this allows us to navigate better within reciprocal space. It allows us to see where other reflections are and understand better what our particular orientation of our crystal is. Okay. Having said that, let's get into the mathematics now of diffraction. Structure factors. Before I talk about structure factors, I just want to give you a geometric understanding of what's happening when waves are being scattered off atoms within a unit cell. So here we're looking at a projection, in this particular case, of a body-centered cubic cell. We're looking down one axis of the cube, and we're looking at the projection of the atoms on that cube. So these correspond, there's an array of atoms which are scattering the electrons at particular angles, and here I've set up the Bragg angle. So if we look at the blue waves here, we have constructive interference at this particular angle for atoms which are scattered off these layers, the dashed lines, shown by the dashed lines, so here and here. Now it turns out that in the body-centered cubic lattice, there are equal number of atoms on planes which are midway between these two planes. So if our Bragg diffraction is set up to be consistent with coherency for reflection from the plane which is defined by the one or all Miller indices, it turns out that for the planes which would otherwise be on the two or all planes defined by the two or plane spacing, that they're actually, when you at that same angle, they're scattering at which are at an angle, with a phase such that these waves cancel with these waves. So we're exactly 180 degrees out of phase. And for that reason, when we have this Bragg condition set up so that the diffracting vector in wave space coincides with the reciprocal lattice vector, which corresponds with 1 over d, in fact, you don't get any intensity because it all cancels. And that spacing here, we can see clearly it's just a half of the distance between here and here. That spacing, formally, you define it by taking the coordinates of the atom within the unit cell, defined by this cube. You take the coordinates of those atoms, and you take the dot product with the diffracting vector, when the diffracting vector is perpendicular to the plane. And it has a magnitude of 1 over d. So that if we take the dot product, we actually get a real number and a reciprocal number, and we end up with a fraction. In this case, it would be a half. And that half defines the phase difference between the two. So when we multiply it, when we represent that phase as 2 pi and multiply it by this dot product, which is a half, then we get the phase difference from the scattering from that atom is pi, which is 180 degrees. Again, a lot to assimilate. It gets a little bit more complicated when you look at the hexagonal structure because the atoms are not exactly halfway up between different planes. And if we're talking about setting up the diffraction conditions for these planes, the prism planes, for instance, and we look at, and this is the unit cell, and we look at scattering from the atom within that the intermediate place has the same atomic density. You just take my word for it. I demonstrate that in one of the lectures, but I'm not showing the camera right now. Just know that this is the same. There is equal planar density of atoms for these atoms here at this location there are for these atoms which define the corners of this unit cell. In that case, the R dot G factor is 1/3, in which case the waves for the Bragg condition for these planes given by D100, the scattering difference for the atoms at this location, intermediate location at 1/3, 2/3, 1/2, is actually 120 degrees. So we can use that as when manipulating all of this information. It's typical to represent the waves by an exponential form. An exponential form, you can do that because you have the Euler equation, where you can represent a wave, which we've been talking about it here in terms of sinusoidal or cosine variation in amplitude. If we represent it in this way, A cos theta plus I sine theta, we have a real and an imaginary part. It turns out convenient mathematically, especially when you're doing differentiation, to represent the wave in this form. And then one can simply take the real part if you want, or the imaginary part if it suits, after you've done some manipulations. And the part that we're interested in, theta here, is the phase difference. We're interested in the phase, or if you like, the phase of the wave relative to some baseline value. And as I said earlier in the previous slide, this is 2 pi g dot r, where r is the location of the atom in the unit cell and g is the diffracting vector. And we can sum up all of the interactions, the phases, or if you like, we can sum up all of these waves just simply by summing up by this sum. The phase shift, this is useful now because the phase shift, you can introduce a phase shift. If you're working with this wave here, for instance, we can introduce a phase shift simply by multiplying by another Euler number with some factor. And then the exponent, you can just add the exponent when you multiply by another Euler number. Where this becomes important, as you'll see later, is when it comes to scattering. Because when you're considering scattering, it's often considered to be involve a 90-degree phase shift. And and what that means is that the cosine, something which would have been a cosine, then becomes a sine, and we can sample that and bring it into real space simply by multiplying by I. I know, a lot to assimilate. It might become more obvious later on. So I've scribbled something here from Cullity, where he explains about why how this, if you like, the link between representing waves, which you see here, which have different amplitudes, the varying, but they also may have a different shift in their phase, one relative to the other. And when one is looking at interference effects, one is simply adding these waves at each location, and we can do that by looking at this angular relative phases and sum up the magnitudes of the vectors that result. And that can also be done using a Argand diagram if we represent the vector, the wave, in terms of an Euler number. The beauty of using Euler numbers is that we can look at the intensity of the wave, and the intensity of a wave is basically the square of the amplitude. And then when we've represented the wave as an Euler number, we can determine this intensity by taking the number with a complex conjugate, multiply it by a complex conjugate, and you get the same value, a squared. I mentioned that the beauty of using this form of using an exponential form is that, well, there are two things to note here. One is, in using an exponential form, we can multiply by some shift in the phase of the original wave. And in that case, the expanded form becomes cos theta plus delta theta, sine theta plus delta theta, if the shift is represented by delta theta. And another feature which comes into play when considering diffraction, dynamical diffraction theory, is that the A, your multiplier, your amplitude, itself can be a complex number. And when it's a complex number, the parts that are complex actually end up multiplying by the sine, extract the sine component. So if this A is a complex number, which is, let's say, A plus IB, then the IB part, when you multiply it by the Euler number, which represents the wave in this form, you're actually extracting the sine component. You moving the sine value of the Euler number from imaginary space into real space, and that would then represent the scattered wave. So that's becomes kind of important. It's something, if you read texts, it will be presented as a given, but it's not obvious to most people. Certainly, if you didn't study physics, you'd be or math, or applied mathematics at a higher degree level, you wouldn't necessarily have a strong familiarity with that, and it's frustrating when you get lectures in electron microscopy and it's just understood that you understand that. Anyway, multiplication by I extracts the sine component. Moving backwards a little bit now, I mentioned about one can sum up all of the scattering from different planes in the unit cell, the plane being represented by the diffracting vector, which is the equivalent of a reciprocal lattice vector, which is of length 1 over d and direction perpendicular to the plane, and the different atoms in the unit cell. So if we sum over all the atoms in the unit cell, we get a net value for the scattering factor. Fn here is just the individual scattering from a single atom. So Fn doesn't necessarily have to be the same. It doesn't have to be in a single crystal, it'd be all the same atoms, and all the FNs would be the same. But in something like an ordered solution, such as gamma prime in a nickel alloy, these FNs depends on the atom position. The scattering, the atomic scattering factor will vary because you might have an aluminum atom or a nickel atom and still have a face-centered cubic cell. I'm not sure whether I've forgotten whether I include a little bit of that in this lecture. I don't think I do, but just be aware of that. So if we have an atomic position which defined by the fractional coordinates x, y, and z on the lattice, the principal lattice basis A, B, C, we have a corresponding reciprocal lattice basis A star, B star, C star, and we also have fractional values which define the reciprocal lattice vector, or the G vector, the wave vector defined by the Bragg condition for that plane. If we take those two numbers and we plop them in this equation, which is basically a number which is the intensity of the scattering for different planes from a unit cell, the phase factor is the product of these fractional numbers, h and xn, k, yn, l, and zn. So where do we use that, or when does that become obvious? Well, if we look at a body-centered cubic lattice, I mentioned previously how I showed just with the waves how interference, you get destructive interference if you set up your diffraction conditions such that these planes here, the 100 planes, are shaded in, actually it's all 10 planes. I've not labeled that right. That's why I think, let's assume that's an X. Look, X axis here. Let's assume that this is a 10 plane and labeled in red. Because we have an equal number of atomic density on the plane, which is halfway in between, you get destructive interference, and the condition then for this case would get has a zero structure factor. Likewise for the FCC, the 100 has a zero structure factor. Conversely, what that means is that the 200, this is displaced here, the 200 will still have strong diffraction. Gets more complicated with the hexagonal close packed, especially when we're using the Euler form to define the phase factors, the G dot R bit. But suffice to say that when it comes to hexagonals, if you read Cullity, you'll see that the best way to show what the F factor is to work with the intensity. So to convert the imaginary numbers, the Euler numbers, you look at the intensity, and that way we can back out what the amplitude is. Not going to dwell on that. All of this can be picked up if you read these books, Hirsch, Howie, Whelan, Nicholson, and Pashley. I've taken a liberty here and rearranged the names because I can then call it HHWNP, which is as it was introduced to me when I was a student. More recent book, which essentially takes a lot of what these guys developed back in That should be 1965. Apologies. Back in 1965, and adds more to it in the context of modern times with modern equipment and advances in understanding. So it takes a lot of what these guys did and puts it in a new book. It was published in 2009. I think there's a second edition out in 2016. I'm not sure. But Williams and Carter, that's a very good book to refer to. And when it comes to defect analysis, my old supervisors here, Loretto and Smallman, they produced a very nice book which is useful for students of electron microscopy who only want to use the fact that diffraction occurs or Bragg diffraction occurs in order to analyze microstructures. Oh, here we go, Bragg diffraction again. Oh, I think this is where, because I'm starting to get more into the theory. Again, just a reminder what Bragg diffraction is: simply superposition of the waves for different conditions, angular orientations of the incoming and outgoing waves. So, okay, move a little bit off now, more to do with diffraction in the TEM, which is related to the TEM itself, not so much the material. So we're going to, but it's still the same principles. Superposition still applies. And what you come across when you're imaging or doing defect analysis, there is a thing called Fresnel, which is the near field diffraction effect, and Fraunhofer, which is the far field. So what we're simply looking at, if I can demonstrate with respect to the Fraunhofer case, if we think about an aperture and the light coming through an aperture, or sorry, the waves coming through an aperture, if you think about Huygens principle, where you can look at each point on the aperture, then you have this. You can sum up all the waves as they go at some location on the back focal plane. I'm just going to pause this for a second. Somebody was just snow blowing my driveway there. I just went out to thank him. Okay, get back to it because I don't want to finish. It gets too choppy if I keep interrupting this. The optics of apertures and in an electron microscope rely on superposition. So if one applies the Huygens principle and splits up each point across an aperture and considers each point as a source of waves which are emitted radially, then at a given angle on some plane, you can choose this plane any way you want, at some point you get a distribution of intensities, and that distribution of intensities reflects the superposition of the waves because of the different path lengths that they take. If we can consider the direct superposition from which would be the case in X-ray diffraction, we could think about this in X-ray diffraction, although this would be a very large angular range and we'd be sampling the intensities. But when it comes to electron microscopy, we're making use of lenses, and what we're basically doing is, by using a lens, we can focus rays that are coming off at the same angle, and it gives you the same answer in effect, and focus them to a point on the back focal plane at the imaging plane where we see a diffraction pattern, and that's one of the benefits of using the lenses in an electron microscope. We can reduce the range, if you like, the angular range. We can select waves that are coming out at specific angles. It turns out to be very similar to the, or essentially the same as what you have here for if you don't have a lens in the place. But thinking about just simply, one can use any kind of MathCAD or MATLAB and reproduce this very easily. You just simply split up your length between the edges of the aperture, assign each point as a source, and then sum up the intensities where they superimpose at some different point. And when you do that, you get some kind of distribution depending on where you are relative to this aperture. So you move this line closer or further, and what you do is you see oscillations. Well, you see a difference in the distribution of the intensity as you get closer, but this, what you find is that as you move this plane where you're sampling, this peak actually will oscillate between negative and positive, because you can see how you get into conditions of destructive interference at certain points. Or these peaks certainly would oscillate between that. So, I've just said that. So this is what I'm talking about. Just we're taking taking different points within the aperture, look at the distance, and then simulate what that would mean in terms of a superposition of the waves at each given point. So these are essentially the diffracted waves, and this is the direct beam. So when it comes to Fresnel imaging, so where this effect becomes important, I mean, the Fraunhofer effect is not such a big deal. We don't care about it too much when it comes to the far field, because we already know that the diffraction pattern is simply a representation of reciprocal space. But when it comes to the near field imaging, we use the Fraunhofer effect, we have to consider the Fraunhofer effect. What do I mean by that? If we're looking at cavities, we can consider them as small holes or small apertures through which you have through which you're shining your radiation. So we're doing that, and we've got this got these cavities, and we're looking at the distribution of the intensity at some location away from in front of the aperture. And if we vary the distance slightly, like a fraction of a nanometer, in this particular case, we go from in a condition where we have a bright peak, like here, or a bright image, or a dark image, as we have here. And at the point of focus, if you like, there is very little intensity. Now, this is useful to some extent if you're looking at small cavities, because it might make it easier then to see the cavities. If you go through focus, you can see these points going from bright to dark. But a word of caution: contamination on the surface looks the same as cavities. So here's some pictures from 2.5 niobium pressure tubing. Zirconium alloys don't have cavities, or very rarely, especially Zirc 2.5 niobium. pressure tubing because zirconium doesn't produce helium, and we don't have the conditions, certainly in reactor operation, we don't have the conditions to create cavities during irradiation. But when you polish the sample, you often leave residue on the surface, contamination. In this case, it's kind of like an amorphous niobium-rich oxide. And this shows up with Fresnel contrast. So this is a surface deposit. And we have the same Fresnel contrast, and you can see that this isn't a cavity, it's a little string of something, a little wormy structure. These wormy structures exist from the contamination and would show up bright or dark, depending. Now, the more circular ones, which you might mistake for a cavity, also show up in the same vein as bright or dark. Now, the reason that there are two points here. One, if one is examining a material and one looks at that and you see, oh, Fresnel contrast, this is a cavity in the material. Not necessarily. Especially if you see it in a wormy kind of structure like this. Not necessarily. It is more than likely contamination in cases where you don't expect cavities. So if you have a sample and you say, oh, I don't expect to see a cavity, and there is this thing that looks like a cavity, check it out, do some stereomicroscopy, and verify for yourself that this is within the foil and not on the surface. So I've used this effect to some value, or in the past, during my studies on zirconium pressure tubing. This is an irradiated piece of zirconium pressure tubing, and during irradiation, the niobium itself forms clusters, small precipitates, and for whatever reason, let's say I'm interested in these precipitates to know what they are and how they formed. So in this field, in these two fields, I can see which ones are the precipitates, which are these black spots. So if we're looking at these black spots here, I can see which ones are precipitates because they're also black spots when imaged up here. They may be a bit fuzzy because we've gone through focus, but let's say this example here, it's black and black, and here's two black and black. Although you're essentially not focusing on these points in this particular case, these are beta niobium precipitates, and they're not contamination. They're not surface contamination. So I've seen so many instances in publications where people see these white dots and say, oh, look, this is Fresnel contrast. We do it through focus imaging, therefore it's a cavity. No, it could be surface contamination. So when you know you have cavities, Fresnel contrast comes into play when you're going through focus in understanding the variation in the focus in a regular image. So here's some cavities, real cavities or helium bubbles in an irradiated Inconel X750 sample. Now I can see the effect of the height difference of these bubbles within the foil, which just by varying the height at a certain focus condition in your microscope, the images might be dark and bright or bright and dark, depending on the height of these bubbles. So without resorting to stereomicroscopy, I know I can decide at what height some of these bubbles are, like all the ones that are dark in this image are at one height within the foil, and all the ones that are dark in this image are at a different height within the foil. So we can use that Fresnel imaging technique to better understand the relative spacing or the relative distribution of real cavities within a foil. Keeping on with the optics now, when it comes to resolution, let's consider depth of field. And I'm going to diverge a little bit from the TEM and talk about some SEM. So SEM images are shown here. This is of the same material. This is Inconel X750. This is the unirradiated case, and this is the irradiated case. So because all those bubbles they're helium-filled bubbles, and helium doesn't get absorbed by grain boundaries. It tends to sit on grain boundaries and stabilize cavities there. You tend to get more intergranular, or a lot more intergranular fracture when you have helium bubbles in a material. Now, in this particular case, there's the image is quite nicely focused here, but it's a little bit fuzzy off to the edges. And partly that is because it has a different height. And depth of field becomes important. Now, in an SEM, the image quality or the resolution of the image is dictated by the spot size, so where it intersects the surface. So when you have a small spot size, let's say that hits the surface at this point, we see a smaller sampling of the surface. And when you have a large spot size and you have a variation in the in the surface height, for instance, this will become less resolved, this variation. So, and there's a range over which you say, well, we can tolerate this amount of resolution difference. And this is what's defined as a depth of field. Depends on the working distance and the aperture size and the magnification, of course. So depth of field, or the resolution is related in part to the focusing ability of the electron optics and getting a small beam, but also it's limited by diffraction effects. So as we showed earlier, we have this peak which shows up from Fraunhofer or even Fresnel diffraction, more the Fraunhofer, whether you have a lens or not, and the peak has a certain width depending on the aperture size. So if we take the semi-angle, convergence angle, which is dictated by the aperture size, and because it's a diffraction effect, there's a limitation on the width of that. The peak one would get, the interference peak, given by the wavelength. There's a limitation then in the resolution as one changes in this case the aperture size. So because we're limited by other things other than diffraction in the SEM, typically the resolution, or if you like, the probe diameter, varies in this range. Now, when it comes to the TEM, the resolution is very much dictated by this line and by diffraction effects. And I'll explain that in a second. So what dictates the resolution in an electron microscope is this Fraunhofer diffraction, where we have a peak width, and the peak width is a function of both the wavelength, amongst other things, but also the aperture. So we have a large aperture, reciprocity comes into play, just as it does with Bragg diffraction, where we have this reciprocal space, where it's the diffraction pattern is the Fourier transform of real space. The peak width here is a Fourier transform of the aperture, and it's small when the aperture is big, and it's large when the aperture is small. And so we want a large aperture for high resolution to image atoms, typically in the electron microscope. The resolution limit is not dictated necessarily by the width of this peak, but by being able to distinguish, when you have overlapping peaks, what is the minimum separation that one can tolerate, where we can still distinguish between these peaks. And that's the expression that dictates this resolution limit is 0.61 times lambda over beta, where beta is the semi-angle of the collection angle of the aperture. Okay, so now we get into the theory. This will be the last part. I introduced, certainly for the case of structure factors, in order to calculate structure factors, that the wave is typically represented by this Euler number. Now, from an academic point of view, the phase, if you like, is some function of the frequency times time, and the distance times some value here, which is a measure of the wavelength or the phase of the wave, and that is 2 pi over lambda. Now, when we talk about electron microscopy, we have a coherent beam of electrons illuminating the sample the whole time. And if you can think about it in terms of a strobe effect, we constantly have this coherent beam which is just there. So in terms of time dependence of the wave, we don't have to worry about it. We're looking at essentially a standing wave, although it's not standing. If you think of it in terms of a strobe, it's a static condition. And so we can forget that. So typically when it comes to electron diffraction and understanding the diffraction effects mathematically, we're generally only interested in the wave number or the wave vector, this k, and the distance. Distance in this case simply being the height within the crystal. One can approximate, even though we're talking about vectors. When it comes down to it, we're only interested in the height, which we call z. So formally, the wave equation describing the amplitude of the electron in a crystal is given by this. It's a sum of the direct wave amplitude and the scattered wave amplitude. So wherever you are in the crystal, you're going to be sampling a bit of both, especially if you're thinking about a column. And why are you doing that? Why would you, even though this is a direct beam, if you like, and a diffracted beam, why do you think of them as being coupled? Because they are coupled. I mentioned in X-ray diffraction how one could think of the diffraction as simply single scattering events. So when an X-ray photon is interacting with an atom and it gets scattered, that's it. You then think about where the X-ray ends up and what the phase of the photon is at the point at which it's detected compared to other photons coming in. In an electron microscope, in a material with electron diffraction, it's slightly different because, well, it's a lot different because the electrons interact so strongly with the crystal that when they're diffracted, they can all then rediffract and then interfere with the direct beam. So what actually happens is that you end up with a coupling of the diffracted wave and the direct wave. So this is the wave amplitudes here are represented by phi, and the wave equation or the phase is represented by this Euler equation here. In this particular case, the deviation from the Bragg condition is represented by Sz. Z is a distance in real space going down the crystal, and S is a distance in reciprocal space, which is the deviation from the diffraction condition. That is the deviation of the diffracting vector of a normal plane and the Ewald sphere. G and R in this case are an additional phase shift caused by distortions in the crystal. It can either come from a stacking fault or a dislocation. So it's the same kind of relation that occurs when you're building up a structure factor based on the position of the atom within a unit cell. But in this particular case, we've already dealt with that. We're already considering that we're getting a strong diffracted wave where all of that is taken into account. And then we're looking at other effects now. So deviation from the Bragg condition, as said, and the effect of defects, which in fact change the deviation from the Bragg condition. So, but introduce a phase factor. Now, one of the early attempts to describe this coupling is by representing the diffracted wave amplitude as a combination of the diffracted wave amplitude and some diffracting vector, so that there's some component of the diffracted wave. There's some component of the diffracted wave that feeds back in to the diffracted waves, but there's also the direct wave which feeds into the scattered wave. So this dphi g by dz in this context, relative to the configuration we see here, you'll notice that each component is the denominator. There's this parameter called psi g or psi 0, and this is an extinction length. And this defines the distance in the crystal that the electron is traveling where you might get complete diffraction. Sorry, it actually corresponds to a oscillation in the intensity of which is a full cycle. So we're going from a bright image to a dark contrast, bright to dark to bright. So this intensity will vary down the crystal. And when there's a maximum amount of intensity which is scattered from the direct wave, we've actually traveled half of an extinction distance. So this extinction distance is a measure of how far the electron travels before it's completely being scattered into some other feature. But then it comes back because of the coupling with the diffracted beam. So you can see how, if we look at d phi, the change in the amplitude, let's say of the direct beam or the scattered beam, the change in the amplitude is some if you like, is dz over psi g. It happens over a certain distance where you get a change for whatever reason. You get some change in the amplitude because of diffraction effects, which are dictated by and the distance over which this occurs. Like say 100% distance is psi g, and dz says what fraction of this 1 over psi g we're considering at each step as we proceed down the crystal, through the crystal. Now it turns out that when Hirsch, Howie, Wheeler, Nixon, and Pashley wrote their book, in it they make the point that they can't get this equation to work. It doesn't give the variation in electron intensity as a function of either deviation parameter or distance in the crystal, or that one would observe. So it didn't match observations, and it didn't lend itself to easy solutions. And what they found was that they could get agreement with the observations by applying a modification to this, and this is the modification that they applied. They, in effect, split the amplitude into a real and an imaginary part of different amplitude, of different amplitudes, because you have different extinction lengths that are in the imaginary component. So they found that they had to do this in order to get the agreement with what's observed. And what are we talking about? What's observed is the variation in the intensity as you go down the crystal for different combinations of these extinction distances, and also the variation as one moves between S positive and S negative. So, and this is directly from Hirsch, Howie, Wheeler, Nicholson, and Pashley. In order to solve the equation, what they did is they made some substitutions, some phase shifts to simplify the solution, and they ended up by simplifying these equations into this form in terms of the Howie-Wheeler equations, but the Hirsch, Howie, Wheeler, Nixon, and Pashley equation, it becomes in a simpler form like this. You'll notice that the S and the deviation from G, or the scattering effect of defects, dislocations, and stacking faults, it's not, when you make these substitutions, it's extracted from the exponential form, and it just becomes a multiplier in this particular case to some new wave amplitude. So taking this equation, we then want to look at the solution to this equation, and you can do this numerically. So in my case, I used MathCAD. I plugged it into a Runge-Kutta routine. Where, oh, look at that. This is cut off here. Where this array here represents the starting conditions for the real part of the direct beam, the imaginary part of the direct beam, the real part of the diffracted beam, and the imaginary part of the diffracted beam. And within MathCAD, there is the Runge-Kutta routine. Using the Runge-Kutta method allows one to step through, take incremental if you like, an iteration, change the dz, change the depth a little bit, and then calculate at each point a new factor which feeds into this array. And but how these different components, the real imaginary parts, how they change depends on the other entries. We have the real and imaginary parts of the direct beam and the real and imaginary parts of the diffracted beam. These parts contain the effect of the dislocation. In this particular case, sorry, I've included a dislocation, and this is the equation that defines what the rotation of the dislocation planes, the effect of the strain from the dislocation has on the phase factor. And here we have the deviation parameter. So when you do it this way, we can, and this is for a simple case of a screw dislocation. And that's in Hirschhauer, Whelan, Nicholson, Plashley. So anyway, you can solve those equations numerically, not analytically, numerically, and get something like this. So these are the two cases, S negative, S positive, just with some random selection of parameters which seem to work. And then if I put in a dislocation at the location 50 units in the thickness, this is an arbitrary length scale, 0 to 100 units, we see the effect on the scattered intensity. So that's one way to do this, the solution to the equation. But as I mentioned earlier, the one can think of the waves or the wave amplitudes for both the direct beam and for the scattered beam as being like a standing wave, or a wave which is, you turn the strobe on and you're freezing it. So the time is factors out, and we're just looking at the distance. But in doing that, we can come up to a solution because it's a static solution for those wave equations. Now it turns out for the defect-free, let's not complicate it now, it's for the defect-free case where there's no dislocations or stacking faults. By manipulation, by substitution of the Hirschhauer equations, it's possible to create a differential equation for each wave, for the amplitude of the direct wave and for the amplitude of the scattered wave. And these equations are analogous to what you would get from a coupled oscillator. And basically, because it's essentially somewhat like a coupled oscillator, you have a wave coming in, some gets scattered, some doesn't, some gets diffracted, some of that diffracted wave gets scattered and some doesn't. And then you look at down this column, you approximate to look at what the effect of varying Z has on the amplitude of these things. In Williams and Carter, and I think the same also applies to Hirschhauer and Whelan, they use the ansatz method to solve these equations. They use basically a complex exponential. They assume that this wave vector is now a complex exponential. And that gives two solutions for each oscillator. So we can think of it pictorial like this. Here's a coupled oscillators. I pulled this off the internet. And you can see how, if we think about a direct wave and the diffracted wave, and they're going down through the crystal, this is as a function of time, but in our case, it was a function of distance in the crystal. These waves are sharing energy back and forward, and the amplitude is varying accordingly. And that's the coupling. That's the coupling effect. Now, this is a mechanical oscillator, coupling of a mechanical oscillator. And it's not quite so simple for us in diffraction, because we have these scattering events which change the phase, and it's not exactly like this. On top of that, the other complication is refraction. Now, when electrons are passing through a material, some of them may be slowed down by the repulsion from other electrons, and that slowing down reduces their wavelength, increases their wave vector. But some of them may be speeded up when they're attracted by the atomic nuclei. So what you end up with is the possibilities of getting two waves. Well, sorry, I shouldn't say two waves. Yes, two waves. And you can think of that in terms of if you how these waves would then interact, the one being slowed down and the one being speeded up. We also then end up, if you superimpose two waves which have slightly different wavelengths, you end up with somewhat similar to this, a situation like this, for which there are two solutions for the wave equation. So you're essentially plugging this thing into that and coming up with a more complicated result. So while a pair of coupled harmonic oscillators serve as a good mechanical analog for kinematical electron diffraction, I didn't mention that it was kinematical, but that's single events, if you like. Dynamical, actually, I'm not even sure that that's correct. Let's just say it's a reasonable mechanical analog. Dynamical diffraction is complicated due to dispersion, because the electrons entering the crystal are scattered, refracted in two possible ways. The electrons are either decelerated or accelerated by the potentials in the crystal. The direct and diffracted waves are then the result of interference of the two resultant waves of different wavelengths. I didn't do a lot with optics when I was a student, but there are some things that one can look up from textbooks on optics or waves. Ignore the top one, which is in frequency space, but this one's now, if you look at this bottom plot in wave space, there's when two waves are superimposed and they're close in wavelength, there's a in terms of the this is an absorption curve, where you can get this. I'm not sure what the absorption is here, but the refraction effect of the waves as we get close to one is shown here, and this shows that you get more absorption here, or destructive interference, and more constructive interference here. But there is a change in the refractive index. Sorry, this is N now. Change in the refractive index, which is negative when the one wave is slightly shorter wavelength than the other, and positive when one wave is like slightly higher than the other. And this is known as anomalous dispersion in the one case and regular dispersion in the other case. So in a non-dispersive medium, or if we're thinking about kinematical electron diffraction, we don't consider the formation of anything of these refracted waves. There's no refraction and weak scattering. And this is how the diffracting vectors would be envisaged in an Ewald sphere construction. You have a beam represented by a wave vector, which is 1 over the wavelength, and then it's diffracted. And the difference between the two beams is the diffracting vector G. Not to assimilate there. But when we think about dispersion, there are two possible waves now. We've created this slowed wave, which has a shorter wavelength, and in terms of the reciprocal space, this amounts to a larger vector for both the direct and the diffracted beam. We have a larger vector than what would be the case for the kinematical case, where you have no dispersion. So these two waves, when you're close to Bragg, are coupled, and we have an interaction. So we have a number of possibilities. We got the direct, so the refracted, what's called a block wave 1, refracted block wave 2 in the direct beam, and then the same, but with this deviation from the diffraction effect, the diffracting vector of G in the diffracted case, which then are summed up, superimposed to give what would be the diffracted intensity. And likewise, if we were looking at the direct intensity, it's the sum of these two waves as they are selected on the backfocal plane of the microscope. So block waves are a natural consequence of refraction, but they're also a natural consequence of what Hirsch, Howey, Wheeler, Nicholson, and Pashley, how they formulated their equations. But remember, Hirsch and company, they had to assume some fudge to make the equations work with no physical relationship. It's just some way to make the equations give you the answer you want. And then when they work through the formulations, it turns out that they have to have two solutions to the wave equations, or multiple solutions, two solutions for the direct beam and two solutions for the diffracted beam, which is exactly this. But that's what one would come up with anyway if one was just simply did a thought experiment and say, what do we have if when our wave coming into the crystal is refracted, but it's refracted into two parts? How do these different two parts then interact when it comes to this coupling effect of the direct beam and the diffracted beam? And this is a pictorial pictorial picture. Of course, it's a pictorial picture. This is the way to think of it in a non-mathematical term. But we end up with this anyway, or Hirsch and company ended up with this picture because they had to apply the fudge factors to make the equations work in the first place. So when I was first introduced to dispersion surfaces and this sort of thing, I didn't understand it. As a student, physics at Bristol University at the Royal Fort, we had a lecturer. His name was A.R. Lang, Professor A.R. Lang, and the first lecture we had, we were introduced to these things. He came in and he drew a circle on the board, and he drew another circle on the board and said, "There's a dispersion surface." And then he proceeded to just talk at the board for the next half an hour, mumbling something about dispersion and diffraction and whatever. And we were all scratching our heads. We go, "What the heck is he talking about?" And I've never really understood block waves until more recently. And then it occurred to me that, oh, we're talking about two real waves, and they can be detected. And this is an image of a block wave, an electron diffraction that I pulled off the internet. They can be detected, and they're real. There are real waves. And once you realize that they're real and they're not some imaginary number, then it becomes much more, or a fudge factor, if you like. Then it becomes much more poignant, and one can understand it and accept it much easier. And if I have to share anything with you, it's that. And I might be wrong. I could be completely out of my mind, but this is how I can rationalize it. The only way I can rationalize everything that Hirsch and company did and put it in, make it sort of make sense physically, is if I start off by thinking in terms of, well, we've got two possible waves here, or two refracted waves, and they can each interact both by being coupled to give a diffracted beam, and yeah, so we end up with this range of possible solutions. The block wave 1 has a larger wave vector, and that's a shorter wavelength because it's slowed by the medium. And block wave 2, which is this bottom one, has a smaller wave vector. It's a longer wavelength because it's accelerated by the medium. So how does this work out formally? Well, we go from representing, as I showed you initially, the wave equation in the crystal being represented by this. It's now represented by a sum of block waves with different multiplying factors. So the block, we have different, these amplitudes, if you like, are a function of the deviation parameters. But block wave 1, so for whether you talk about, I should mention that this really is for, yeah, so block wave 1 is some combination of these diffracting conditions. Block wave 2 is given by that. So these are the solutions to the differential equations which were put together in order to fit the observations. Okay, so the two block waves have wavelengths which are greater and smaller than the incoming waves. I've mentioned that already, so I don't have to talk about that anymore. Okay, so finally, the last point I want to make is in textbooks, you'll see this kind of representation of the block waves. Block waves corresponding, in this case, it's the 1 and the 2 here. So we have block wave 1, which is the one that's slowed, and block wave 2, which is the one that's speeded up. So traditionally accepted, block wave 1 is the one that's absorbed the most for a negative deviation from the Bragg condition. And it's generally assumed that's because this is the one that interacts with the atomic nuclei and is therefore more absorbed for this S negative condition. While it's traditionally assumed that block wave 2 is the one traveling down between the atom nuclei. But I'm not so sure that this is the right picture. Is it correct? Well, according to what I just explained there, where I could think of block wave 2, which is the smaller wave vector and therefore larger wavelength, this would come about physically. You can envisage what block wave 2 is about by it being accelerated. And block wave 1 is the one that's decelerated when it comes into the crystal. So what I think is probably a better picture is this one is the one, block wave 2 is the one that's going close to the atomic nuclei and is being accelerated, but it's not being absorbed by the nuclei. I mean, the nuclei themselves, physically, the cross-section is very small. So it goes whizzing past, like a gravity assist, if you like. And we end up with little absorption, but we do get the slowing effect for block wave 2. Now, whereas block wave 1 is, let's say it's traveling through the electron cloud surrounding the atomic nuclei, and it is absorbed. The reason to think of this as being the more feasible picture, being absorbed, is absorption is a bit of a misnomer, because in the context of an electron microscope, if you have a big thick piece of material and you shine electrons through it and the image is just basically dark, it's not because the electrons are all sopped up by the material. It's because the electrons are scattered out away from the optic axis. They're scattered into the sides of the microscope. So absorption in that context is really more scattering. And I could rationalize that in this picture simply by saying the nuclei are very small, and therefore you get less scattering, but more acceleration. But here, when the block wave is traveling down between the planes of the atoms within the electron cloud, which is the bonding electrons, the valence electrons, and the bound electrons, and the bound electrons as well. Whatever, you've got a lot more events happening, a lot more scattering events, and therefore more absorption happening here. So we end up with these two equations, essentially that lead you to this picture of the two block waves in the crystal. And that comes about because we had to make, or Hirsch and Company had to make certain assumptions about the equations and how they could manipulate them or reformulate them or make them agree with the experiment. So they become, in effect, empirical equations. So to finish now, I'm just going to read this. Electrons traveling in a crystal potential can be represented by simultaneous equations that are similar to the mechanical analog of coupled oscillators. This inevitably results in a solution for the two oscillators, the direct and diffracted waves. That is a combination of the two solutions for each quadratic equation derived for each oscillator. The coupled simultaneous equations describe what is observed and imply that there are two solutions, block waves that can be combined to describe the variations in amplitude of each oscillator. But which came first? If one looks at the equations that are formulated, we end up with two block waves being the result. But which came first? Refraction acts on the direct and diffracted beams, producing two separate real electron waves that then travel through the crystal. The description of the total electron intensity is the function of scattering angle and distance traveled in terms of coupled equations follows. So you going at it from the reverse direction, you'd get the same answer. My math isn't good enough my brain hurts too much to to try and do that. But I'm just sharing with you a way I can rationalize this. It helps me understand what's going on. And when I just take things on faith, as I have had to do over many years, before I realize, oh, maybe these waves are actually real waves. Once I realize that for myself, I can accept this, and it doesn't frighten me anymore. So I like the idea of the two refracted waves, and I like the idea that we aim to that solution by two separate routes. In the one route, which is the one that I can handle, is the physical consideration of refraction, and the other route is by making these what in effect turns out to be empirical solutions to fit the observations. One ends up at the same picture, that you have to have in effect two waves for each wave vector in the crystal, one being the direct wave vector and the diffracted wave vector. They're each separated into two components, which are from block wave 1 and block wave 2. And you couple them all together, and you, by some further manipulation, you can rationalize what you get. I'm comfortable with that. Okay, so this came from a lecture I gave recently, which shows some. It's just some things from YouTube that I put together, showing slip and defects in crystals. But the bottom one here is of value because it's something I saw on YouTube, which explains the refraction, especially with electrons. So it's a good one. And that's all I have to say now. Thank you.